All right. Conditional probability. It has been said by some people that teach math that all probability is conditional. There's some condition on it. But this will prove important. There are a few notations that some people do a little bit differently, but then some that kind of stay the same. So we'll hopefully be able to make that distinction for you. Some of the notation is probably going to be what's most important here. So basically, it's the probability of an event occurring given that another event has already occurred. So that condition is basically that that other event has already occurred, right? And notated, that's probably pretty important to look at it that way. That's probability B given A is how you would read that. So that's probably important to get most of that down, actually, at least the notation and how you would read it to somebody. So that way, as I read it the rest of the year that way, you can understand what I'm talking about. And then we'll take a look at this first example to kind of try and iron that out for you. This is actually a pretty important section to understanding probability. No, I mean just this is very important. Yes. Without this, you can't get the rest. All right, so example 1 says 2 cards are selected from a standard deck at random. Find the probability that the second card will be a queen given that the first card is a king. We're going to say that the king was not replaced in this particular one because that's always a question. Was that one put back in or not? And here we're going to say that. So basically how we could write this one is we want to find the probability. Well, how would you write that? Let's see if you can do it. What would you say? What's kind of given here? Where would it go? Things like that. What do I really want to know? Okay, so what should I put? If I'm trying to put it in this notation here, let's say Q is queen and K is king, what should I write? Q slash, yep. So it's saying what's the probability of getting a queen given that I know I already have a king. So is that what we want to say? Exactly, that's perfect. Okay, so that's how we want to do that. Well, that looks a little weird now, but that's okay. There we go. All right, so do I want both of them to happen? Is that what I'm saying in this question? Or do I just really want the second one to happen? So let's just go ahead and figure out, well, for the king, and let's face it, if it's a standard deck of cards, we're going to say without jokers, there are how many cards? 52, correct? How many of them are kings? 4. How many of them are queens? 4, okay. So you're saying getting that king, maybe, let's say I asked you only for the probability of getting a king, so that would be something like this, right? What is that? That's 4. And we don't have to worry. Obviously, that's one. We don't have to simplify. Okay. So, what's then the probability after that happens of getting? Because we know that happens. That's already happened. That's done, right? So how would you go and get the queen then? Yeah. Perfect. 4 out of 51. Because is there still 4 queens in there? Yeah. There's 4. Basically, your sample space there is getting those queens, and it doesn't matter which are the queen of hearts, the queen of spades. That's your sample space of being successful. But how many that you can draw from has changed. There's only 51. Okay. So any questions on that? How to kind of go through that in your head? How that works out? Now, are those 2 fractions incredibly close if you go to decimals? 4 over 51 and 4 over 52? And that's something we'll have to discuss as time goes on in this chapter, as whether is that good enough or not. Okay, and we'll have to discuss that as we go. Once we get to hypothesis testing. Sounds really cool. It's kind of hard. All right. This one here is huge. Independent events. Independent events. Many of you have a very good kind of an idea of what that means, but I think we're going to really make it more concrete here. All right? And so I probably should have given myself more room. So I will. I probably could have done this a lot quicker, but oh well. Independent events. Some people say basically that one event does not affect another. Well, that's close. There's a key word. Oh, wow, that's horrible. Probability. The occurrence of one event does not affect the probability of the occurrence of the other event. So basically, like that last problem we had, did one event affect the probability of the second event in the example we just had? Did the probability of getting a queen change? It did. It went from 4 out of 52 to 4 out of 51 real quick, didn't it? So those are not independent events. And one notation that you're going to see a lot here then is basically, if I find out something like that, is it the same as that? That's what you really want to know. Is the probability of B given A the same as the probability of just B all by itself? If it is, guess what? Did A really affect it? No. You see, you get that? That makes sense, doesn't it? Obviously, you could flip that around. You know, probability of A given B is equal to the probability of A. Okay. Basically, in that case, it would say that B didn't affect it at all. Okay. So that's huge. You might even want to add that to your definition up there, something like that. That basically knowing what A was didn't affect that. No, that's just me talking. I used example 1 as a reference here. Did knowing that a king was drawn affect? So basically, probability of B given A was 4 out of 51, correct? And this one, if I just would have looked at probability B, king never happened, it'd be 4 out of 52, agreed, in that first example. So were they independent? No, because they didn't equal. They have to equal. Yep, that's huge. But what happens is statisticians kind of cheat a little bit as things go on, okay? And I'll explain why. Okay, so those two not the same from that first example, so no good. And dependent events is actually quite simple. You know, there's always, whenever they're opposites of each other, there's one difficult definition, and then the other one is quite simple. Events that are not independent. So, for example 1, those were dependent events. Remember, an event is one or more outcomes from the sample space, right? That's what that means. So why don't you take a second or two and decide if you believe that these situations are independent or dependent on each other. And when I do it, I'm actually going to do the probability thing to show you how that works, because I think it's that important. And I can even use B and A if you would like, you know, or maybe for this one we can, you know, again, K and Q or whatever you want to use, but I think that we should probably talk about it that way. So do you want to do like Q and K again? Is that how most of you are doing it, or is that how we should do it? Okay. So here we want the probability, well, let's read it. Selecting a king from a standard deck without replacement, and then selecting a queen. So basically this is example 1, right? That's why we kind of did that one. So what should I write here for the, in there? Should be probability of getting a queen knowing that I got a king is, well, we just did that, right? It's 4 out of 51. Is that the same as just that, knowing nothing? Not having done anything, is that probability of Q the same as Q knowing B? No, it's not. We just talked about that, right? So these two, not the same number. So, dependent. So what do we got here? Tossing a coin and getting heads, followed by a tail. So probability here is T knowing that I got H, right? That's how you want to do it? And well, what is that? I mean, so what is the probability? Is it still a half? Yeah, it's 1 out of 2, right? How about the probability? Now, which one should I look for then for this to work out? Tail, right? That's the one. So did getting a head first affect the probability of getting that tail? No, it didn't, because it's still just 1/2. So this is independent. How about selecting a jack from a deck, replacing it, and selecting another jack? So this is kind of hard, but you can do that pretty, just notational wise. Well, that looks very difficult. So how can I notationally kind of help myself out here? Yeah, then should I do it like squared or No, probably subscript would be better, right? So where should the 2 go for subscript? On the first one here, the one on the left, or the one on the right? So I'm doing J2 is the one on the left, okay? And J1's here then? Okay. Well, what is that? So I know a jack got, but then it got put back in, so then that second one is 4 to 52, right? Okay. So what is the probability, and now what should I put here? It's obviously a J, but J2, okay. And what is it? So what do you think? Independent. Now, did most of you probably, did most of you have those answers without doing the probabilities? I'm assuming you did, okay. But as things get more complicated, you're really going to want to, again, focus on that. Okay, it's huge. Any questions on that? Doing pretty good? Now, the reason we want to know if it's independent or not is that way it tells us which one of these formulas I need to use. If it's independent, I get to use a much easier one. It's the one on the bottom. If not, so we're saying events A and B will occur in sequence. So A happens, then B happens. Again, have we said the word and yet? Not really, not in there. We've said A knowing B. We've said that, but we haven't said both of them happening. So if you want both of them to happen in that sequence, basically you would find the probability of the first one times the probability of the second one knowing the first one. Now, are there times that that second one knowing the first one is just going to be the second one? It is, and that's when they're independent, and that's when you can just go ahead and multiply. So which of the 2 do we want to happen? Do we want them to be independent or dependent? It's best if they're independent because the formula is so much easier. Okay, and that's why I say sometimes statisticians will say, well, they're pretty much independent, so I'm just going to use that one. All right, and so that's where hypothesis testing will come in, and we'll have to come back to this and talk about it then. So let's try one. Find the probability of the following. Selecting a king. Oh, hey, we've seen this one. Followed by a queen from a standard deck of cards without replacement. So we've done this one a lot. Well, let's see if we can actually find the probability of both of those happening. So now what do I write? Do I write the little slash? No, you put and. Right? Now, what do you think? We just talked. What did we just say in that last page? Are these independent or dependent? Dependent. So can I use the first formula second? I mean, what's the deal? I have to use that first one, right? So what I basically have to do is find the probability of getting a king. Now, you don't have to write all this if you don't want to, but probability of then getting a queen knowing I got a king, right? So what is that probability of getting a king? We've done this problem so many times, you're probably getting tired of it. Right, 4 out of 52, right? Right, so what is the probability of a queen knowing that you had a king? 4 out of 51. And again, I keep going back to that one because it's one we've done, so you're familiar with it, so you're not afraid of it. And of course, you use your calculators, you do all that fun stuff, or you just kind of simplify on your own, like that. And you get 4 out of 663, I believe, isn't it? Yeah. Which is approximately 0.006. Yeah, or we could all just do it 663 times and see if it happens 4 times. Yeah. But remember, that's where the law of large numbers comes in, that could very well, we could all get very different numbers. We could do it 663 times and it could happen once for you. Or it could happen 10 times for one of you, right? But if we put all your numbers together, then that probably gets even closer to the actual classical number, right? Because you're just more trials. How about tossing a coin and getting 3 tails in a row? Ooh. So probability of tail and tail and tail, right? So again, it'd be tail 1, 2, and 3, we'll call it, huh? Now, technically, what you would have to do if you went with that formula is you would have to do tail 1 and tail 2 together first, okay? And then take that answer with tail 3. But what's lovely about these 3 particular events? They are independent. So do I have to do all that mumbo jumbo? Nope, I can just basically take the probability of tail 1 times the probability of tail 2 times the probability of tail 3, because there is no dependence on one or the other. And of course, what is each one of those probabilities? 1/2 times 1/2 times 1/2, otherwise known as 1/2 cubed, which is 1/8. Number 3 is a very similar problem. Why don't you do that one quick? Again, I want you working on some of the notation too, just so that when I use it later, it doesn't get confusing. So that's one way I could write it. Do you need to use that version of the formula? How come? Why? Ah, you put it back in. So it is okay just to say probability of k times the probability of j, because really isn't that going to come out to be the same thing anyway? I mean, it really isn't going to affect it. And so basically you're taking 4 out of 52 times 4 out of 52. And if I were you, it's way easier just to simplify before you go, right? It's 1 out of 13 and 1 out of 13. It just speeds things up so much. Right? Which is, amazingly, if you round it, now is it the same? So is the first one and the third one dependent or independent? You know, I'm just saying together, if you did the first one versus the third one, they come to the same probability, don't they? Roughly. But are they close enough is the question. And we're going to deal with that much later this year. Okay? So no coincidence that those two come out very close to the same. All righty. We're just going to keep going here. And then we're almost done. Good thing, because the bell's going to ring soon. A coin is tossed and a die is rolled. Or, excuse me, a number cube. Calculate the probability of getting a head and then rolling a 2. Is it okay to use that second version of the formula? Yeah, it's fine. Because those two are completely independent. Right? So what is the probability of getting a head? And then rolling a 2. 1/6. Right? So you're saying I can just go ahead and multiply them separately? You're right. 1/12. The probability that a salmon swims successfully through a dam is 0.85, so pretty good, really, 85%. Calculate the probability that 3 salmon swim successfully through the dam. Dependent, independent? Yeah, the one salmon is not saying, hey, follow me, all right? And so basically you can just go ahead and take 0.85. No, because it's 3 of them. Completely 3 separate events. I want to know what's the probability that 3 of the salmon swim successfully through the dam. This is basically just 1 salmon gets through it. So you take 0.85 and basically just cube it, right? Is that exact? No? 0.61-ish, you're saying? So calculate the probability that none of the salmon get through successfully. How do you do that? What do you mean opposite? Very good. Find that complement, or the difference between 1 and 0.85. which is 0.15, correct? I kept the numbers pretty straightforward, right? So 0.15 chance it didn't get through. Same for this poor guy, and unfortunately that guy too. So they're having a rough day. So wouldn't you expect those two last answers to add to 1? Well, they don't even come close. Why is that? Close. How come it doesn't even get close? Because 1 means basically everything was taken into consideration, right? Are those the only two things that can happen with 3 salmon? The first one can make it, the second one doesn't, the third, okay, so that's why it doesn't add to 1. Okay, right? And all those other possibilities. The first one makes it, the second one makes it, the third guy doesn't make it. All right, so there's a lot of possibilities in that sample space that we have not considered, correct? If we're talking 3 salmon, that's why it doesn't add to 1, okay? And calculate the probability that at least one of the salmon is successful in the swimming through the dam. There's a long way and a short way of doing that problem. What is the short way then? Yeah, take 1 minus C. Because that says none of them make it. And you agree that at least 1 means 1, 2, or 3 of them can make it. Is that the complement of C? Yeah, it is. Obviously, otherwise you'd have to sit there and do all the combinations. The first one makes it, the second one doesn't. Okay, let's say this is quicker, right? Yeah. So you do 1 minus 0.003, which was incredibly difficult math that none of us can possibly handle. Does that seem high? At least one of them makes it when the chance of one of them make it is 0.85. So, and 3 of them are going. 3 of them are trying. Does that seem high? Even if it's only 85% for just one of them making it? Yeah, I'm not sure salmon are that smart. But for all 3 to make it, it's only 0.61. Oh, okay.